I'm going to use that in a bit. So we're talking about these automorphisms. So I wanted to look at another example. We talked about this a little bit last time, but let's make sure that we got the details down. Consider this is irreducible. Um, by the way, here's kind of a fun trick, just because everybody likes a fun trick, I think. How do we know it's irreducible? So I make this bold claim. One way that you can do it, so let's do a couple of ways. One way you can do it, and you can cheat a little bit by actually writing down what the roots are, right? So I know everybody loves my math club topic Friday. You can actually use this to figure out what the roots of these are. And the roots, if we consider this over Q, -1 is e to the I pi plus any multiple of 2 pi, right? So I get these roots, e to the I power 4, e to the I 3 power 4, e to the I 5 power 4, and e to the I 7 power 4. And actually, if I was smarter than I am, I might write it this way. I can certainly do that. Everybody agree with that? And after this, the cycle repeats. And the groovy thing about this is this shows you what the complex conjugate pairs are. All right. So this polynomial in the complex numbers is x minus e to the I power 4, x minus e to the I 3 power 4, x minus e to the I minus 3 power 4, and x minus e to the minus. Right, look at that. So if this were reducible in the rationals, you would have to be able to get you'd have to be able to put together some subproduct of this and have it have rational coefficients, right? And notice that the only way to do this, because none of these roots here are rational, right? In fact, they're not even real. Agreed? So the only way that you could ever factor this over, the rationals is if you put the complex conjugate pairs together, right? And if you do that, one of them gives you, and the other one gives you, and notice the coefficients are not, or I'm sorry, not rational. Right, okay with that? That's one way you can do it. Another thing is this is kind of a nifty trick. This one's actually 2 Eisenstein. Doesn't look like it, does it? But it is. Method 2. Place x by equals 1. So this becomes which is polynomial is 2 Eisenstein. Great. So this one can't be factored. But notice, if you could factor this one, then all you'd have to do is replace it, x with t plus 1, and you could factor that one, right? So this transformation doesn't really affect the irreducibility. So that's another way to see that. Everybody okay with that? That's kind of a neat trick, because sometimes things that aren't Eisenstein can be transformed into something that is. Okay, so hmm, this is easy, power of 4, 3 power of 4, 5 power of 4, 7 power of 4. Another way to do this is under a different name. You'll notice if I multiply these two, I get tornadoes to the 8th power, which is going to be 1. And same thing here. Everybody okay with that? So notice that if well, better tell you what F is first. Let F be the smallest field in which this polynomial x to the 4th plus 1 has all 4 of its roots. Now, that is massive overkill, what I've written here, because why?
We just need a tornado.
Actually, right, and any power will do, right? But I'll take the convenient one. So, look at the automorphisms of this. If sigma is in the Galois group of F over Q, then sigma can only go to another root of this. That's it, right? That was kind of one of the big takeaways of last time, is if you have an irreducible polynomial, then any root, if you've got an automorphism that fixes that base field, any root of polynomial has to go to another root. That's it. It can only go to those. And so explicitly, we can list the automorphisms. And let me number these roots, just like we did before. And let's see what the automorphisms do. One automorphism is that. Now notice that once I tell it what to do with tornado, I've told it what to do with every power because it's an automorphism. So this forces your, and this is another choice I have is that, right? And notice what this does. Now, if tornado goes to tornado cubed, that means the tornado cubed goes to tornado cube cube, which is tornado to the 9 Right, so it swaps these. This induces a permutation on the roots, right? In fact, it will give the permutation 1, 2, 3, 4. Given my number in. Agree? What else could we do? So this means so where does tornado to 5 go? It goes tornado to the 5 to the 5. So 25 mod 8, that's 1. How about that? This goes back here as well. And same thing here. Well, it's -3 if you like. This permutation, let's see, this is 1, 3, 2, 4. This one takes tornado to its inverse. And then here. What would that be? 114. Let me make a couple of observations about what happened. Number with the first example that we did right here, this came from adjoining all the roots of x cubed minus 2, right? And notice we got every possible permutation gave me something different. Here we have 4 roots, but we didn't get all possible permutations because there's something restrictive going on here. All the roots are powers of each other. So once you tell one of these where to go, that completely controls everything else, right? And so it's more restricted. But let me notice something about this. The Galois group here thought of this permutation group. What's this isomorphic to? It almost looks like it did in the subgroup, right? Because this comes this. Actually, it's this. You have to do a computation to figure it out. But there's something else that's interesting. Does anybody? This one requires a bit of an eagle eye to see.
U8.
What's that?
Looks like the unit's module 8 with the powers going on.
Well, that's exactly what it is. That right. And when we get to cyclotomic fields, we'll see that. But there's something about S4. Does anybody know another subgroup of S4? It's isomorphic to Z2, Z2. That's too big. Yeah. But I mean, so let me give you another subgroup. There's others. This is also a subgroup of S4, and it's isomorphic to Z2, Z2. Does anybody know what the difference between these two are from a group theoretic point of view? These are isomorphic subgroups of S4, but the top one, the one we got as the Galois group, is transitive. The other one is not. Right? What do I mean by transitive? A subgroup of a permutation group is transitive. Given 2 elements that you're commuting, any 2 you want, there is an element of that subgroup that takes this to this, right? So pick any. So we're what permuting 1, 2, 3, 4, right? 1 goes to 3. Yes, this one, this particular element of the subgroup takes 1 to 3, right? Uh, 3 goes to 1, well, the same one will do it. How about 2 goes to 1? This element will do it, right? This one is not transitive, because for example, if you want 1 to go to 3, you're out of luck, right? There's no element of this subgroup that takes 1 to 3. It is intransitive. Most of the subgroups of S4 that are isomorphic to Z2, Z2 are intransitive, right? You can do 1, 2, 3, 4. You can do 1, 3, 2, 4. You do 1, 4, 2, 3. You all get these subgroups, right? This is the only one that's transitive. And the reason for this is we're going to see this. This is a takeaway. Given any of these 4 roots of this, there has to be an automorphism of the field that takes one of the roots to the other. So pick any of these 2 roots this way. There is an automorphism that takes tornado to tornado minus 3, namely this one. So you always get a transitive. So we'll talk more about that later.
So if it's transitive, it looks like, does it look like the reflections almost?
Well, it just, all it means is you can move freely around. So of course, SN is always transitive, right? Because given any 2 elements of SN, take the numbers A and B, just look at the cycle, or just look at the transposition AB, no problem. AN is also always transitive, right? But most subgroups are, of permutation groups are not transitive, right? I mean, just take S5 and take the subgroup 1, 2. You can't take 3 to 5 that way, right? That's it. And in fact, the number of transitive subgroups up to isomorphism is pretty small compared to the number of subgroups. For S3, the transitive subgroups are S3 and A3. For S4, there's 4 of them. Cyclic of order 4, this one, the dihedral group on the square, A4 and S4. For S5, there's also 5 of them. Cyclic of order 5, dihedral on the pentagon. There's a strange group of order 20, A5 and S5. For S6, I'll stop numbering because there's 16 transitive subgroups, but there's an enormous number of subgroups in the first place. So it's going to turn out that when you have a Galois group, it'll be transitive on roots. So that's something to look for. Here's another question. So for this one, I think we've kind of discovered that the Galois group of F over Q is 2. What about, by the way, does anybody see a subfield of this? So there's Q, and then there's F, Q tornado here. There's actually an intermediate field here. Anybody, let's see what it is.
Which one? Tornado to 4?
What's it now?
The fourth power of something.
I'm sorry, what were the,
Q with the 4th power of tornado.
okay, but the 4th power of this is -1, so that's already Q. Right, so the 4th power of tornado is actually -1, which is already in Q, but you're close.
Oh, the 2nd power.
Yes. QI. Is that it? Are there more? There are actually a couple more. Notice right, so this is really Q adjoined with tornado squared, right? There are 2 more intermediate fields. And how did I know there were two?
Oh, it's Q with minus I is not the same thing as Q with I.
What's that?
Q with minus I is not the same thing as Q with I.
Q minus I is the same. Right, because if you've got I in the field, then you have to have minus I as well.
Maybe you're going to draw the subgroup lattice of nuclear group.
That's an example. Yeah, where do you, anybody know where you get, radical two? Right, so what happens if you take tornado plus tornado inverse? This is
The real part.
cosine pi over 4 plus pi sine pi over 4 plus cosine pi over 4 minus pi sine pi over 4. And this is 2 cosine pi over 4, which is radical 2. That's another intermediate field. Anybody want, yes, there's actually another one.
Square root of minus 2.
That's right. Now, let me ask you this. How many subgroups of C2 are?
Okay, right.
The same. There is. That's a little deceptive, I guess, but so basically this one might be considered to be the group generated by 1, 0. This might be the group generated by 0, 1, and this might be the group generated by 1, 1. And then of course we have the identity. Notice these lattices look alike, and this is not a coincidence. And where do we get these? Well, you might look at fixed fields, right? You might look at automorphisms and what they fix, right? I'm gonna look at a bigger example of this. Let me give you another question. What's the Galois group F? Anybody want to guess that? Galois group, C2, Z2, Q join with this. So now you have to have the automorphisms that fix QI, right? See if you can get that, but it's Z2. Let me ask you another one. One last one, just for fun.
Or reducible, right?
What's that?
Or C2 is reducible, right?
Ah, that's correct. What's the Galois? It's true. Because the root, the only root is 1. Right? And so when you take, so it's a bit of a trick question, wasn't it? When you take Z2 and join 1, it was already there, right? So this is just the Galois group of Z2 over Z2. It's the automorphisms of Z2 that fix Z2. There's only 1, right? Okay, any questions on that? Okay, so let's let me introduce some notation here. I kind of hinted at this. I would suggest that you take this example and the previous one that we did and sort of throw kind of get used to this terminology here by sort of checking what these things turn out to be in these examples. And we'll look at one of them in a moment. So this is a theorem and the definition kind of roll into one, if you will. If you have K inside E inside F for fields, H is a subgroup of the Galois group. I think A. Okay, H is a group. I'm using this notation, this prime notation. When I prime a group, it becomes a field. So what field is this? This is all of the stuff in F such that sigma B for all sigma. And this is an intermediate field. Is a field intermediate to the extension. K inside F. Number B, in this case, I'm starting with E, which is an intermediate field between K and when I prime it, I'm going to get a group. So you prime groups, you get a field, you prime fields, you get a group. This is the set of sigma in the Galois group of F over K. So it's an automorphism of F that fixes K such that sigma of E is equal to E for all E and A. And this is a subgroup of Galois group of F over K. Okay. H prime is called the fixed field of A. Right. Okay, so let me just sketch out this. Okay. Okay. I guess it's clear that H prime is a subset of the field, right? Note that H prime contains K. Right, because just by definition, everything in here fixes K. So this gobbledygook here at least has all K in it. And notice if let's say U and B are in H prime, then sigma of U plus B is sigma U plus sigma B, which is U plus B, and sigma of UB is sigma U sigma B, which is UB. And the same holds true for inverses. So this actually is closed under addition, closed under multiplication, and inverses. I didn't show you that. That's true as well. Okay with that? For this other statement here, this should be a subgroup of the Galois group. Notice, of course, that, the identity is in here, right? The identity automorphism is in E prime, right? Well, let's suppose sigma 1 and sigma 2 are in E prime. So that means that sigma E equals E. Let me point out something else. You gotta love automorphisms, right? Because you can compose this equation with the inverse. E is equal to sigma I inverse. Right? This effectively shows that this is closed under inverses. But let's check this out. Let's do the subgroup criteria. Sigma 1, sigma 2 inverse of E is sigma 1, sigma 2 inverse of E. But by this observation up here, this is E. And by the fact that's it here, this is E. And so this is a subgroup we got a lot of. By the subgroup criteria. Okay, any questions? Let me make a remark here. Well, I kind of look at the fixed fields. I ain't doing this, but I'm gonna erase this board. Well, it's just a sketch after all.
Oh,
Yes,
so all we know now is that when you drew the two pictures, the subgroup lattice next to the subfield lattice, we now know that if you pick a field and one lattice, there's a group in it.
there's something over
We don't yet know that they have the same structure, is that?
That's exactly right. Right. So Ben's right in the fact that we've started building this piece of the puzzle, right? So if we have intermediate fields, then somehow I'm gonna get an intermediate group. If I've got an intermediate group, somehow I'll get an intermediate field, but how they all fit together exactly, it's not quite clear yet. Let me point out. By one, I mean the identity element. So this is the identity automorphism. What's one prime? It's all the stuff in F that's fixed by one. Okay, I know what this is. This is all of F, right? But what's good for the goose may not be good for the gander here in the following sense. But if you look at oops. Actually, I want to look at the top of this, don't I? Right. It is not necessarily that G prime equals K. You know, G is Galois. Because if you have the full Galois group, what do you have here? You've got the Galois group is every automorphism that fixes K. So what do we have here? We have everything in F that is fixed by everything in the Galois group. So what is true is contains. And this containment can be strict. Can anybody think of an example? So this is almost. Let's let F equal Q, adjoin with cube root of 2, and K equal Q. Then the Galois group well, let's see. Can I get this thing to help me? Right, notice that, yeah, I guess this really kind of helps. What is there are only two automorphisms here that, and remember, these are automorphisms in this bigger quote, agreed? Notice in this table, there are only two automorphisms that fix Q, that subfield, right? One of them is the identity, and one of them is complex conjugation, right? Remember this one turned out to be, you can see this one rather dramatically, it's complex conjugation, right? But complex conjugation is not an automorphism. What happens when you take the complex conjugate of something that's real? It's the identity, right? So this is one. So if you look in this example and you compute G prime, this is everything in the field F that's fixed by the identity. So it's everything, which of course strictly contains. And this is actually going to factor into our definition of what we're actually going to call a Galois extension. Okay, any questions so far? The first time I ever saw this seemed like kind of a funny definition to me. But I'm going to put it up here. Definition. Let K and F be fields. We say F is Galois over K if the fixed field of the Galois group of F over K is precisely K. So in this example here, we would say that this field is not Galois because the fixed field of the Galois group is too big, right? It exceeds what it's supposed to be. So it's not Galois over K. Equivalently, F is Galois over K if for all elements that are in F but not K, there exists a sigma in the Galois group, F over K, such that sigma alpha is not equal alpha. I find this equivalent way of stating it sometimes useful. What it means to be Galois is if you have anything that's in F, but it's not in a fixed field K, there's some automorphism that moves it. All right. Okay, any questions on
That science or transitivity from earlier.
that? Well, so to say that, at least in a loose sense. All right, so let me give you an example here. So I did bother putting this table up and everything. Let me give you kind of I'm gonna draw you a picture here that I hope is going to help us with the statement of the theorem, fundamental theorem, Galois theory. Look at this field right here. The smallest field obtained when you adjoin omega, which is primitive cube root of unity, and alpha, which is the cube root of 2. Now, I don't know much, but that's an infinite field. How many fields are there between that field and cube? I mean, at this point in my life, it's not clear to me that it's a finite number, right? I mean, how do you know there aren't infinitely many fields in there, right? I mean, but there actually are only finite many fields. The Galois group is isomorphic to S3. Okay, so we did this in this table by exhaustion, right? I mean, we looked where, okay, where can alpha go? We looked at all these permutations. All the permutations worked out. If you look at the table and tell that they all give you different automorphisms, right? So there's only 6 automorphisms on this field, the fixed cube, right? This means that there actually, it turns out to be a finite subfield. Now, I don't know much. Subfields of this confusing to my pea-sized little brain. However, this I can do, right? So, somebody help me with the subgroups of S3. What are they? I got these. Right.
Oh, yeah, the transitions.
There's a single subgroup of order 3, right? And I'm going to kind of write that explicitly here, consisting of the identity. I'll call this 1, 2, 1, 2, 3, and 1, 3, 2. Right? There are 3 subgroups of order 2. 1, 1, 2, 1, 1, 3. And, you know, looking back on it, maybe I should have written it a little bit because it's quite confusing with this. Back to E you go. And that's it, right? Subgroup of order 1, 3 of order 2, 1 of order 3, and then of course the whole subgroup. And that's kind of it, right? Because those are the only divisors, 6. So the subgroup lattice, I bet if you had 8510 with Macaulay, I'm sure that you saw lots of lattices like this. This is what this looks like. Now, what happens if I look at each of these animals and I do the fixed field? So I'm going to draw the same lattice over here. What I'm going to do is I'm going to do E prime, and I'm going to do this prime. Let's look at the table. It might help. What is E prime? That is, what is the set of elements of the field that's fixed by the identity? It's the entire field. Okay. What's the subfield that is fixed by, let me start with this one. It might be the easiest. Can you look at the subfield and tell me what's the subfield that's fixed by complex conjugation? That is right. this fixes alpha, but notice, the alpha omega and, the alpha squared omega, they're moved. Right? So the only thing fixed by complex conjugation is the real piece. I guess that makes sense, right? Okay, what's the subfield fixed by 1, 3?
Q alpha W. Oh, my God.
I bet it is. Oh, look at that alpha omega. That's beautiful, isn't it? It's fixed. The alpha moves, and the alpha squared omega moves. So this is must be Q. What about what's fixed by? Got what, 1, 2 now? Well, looks like alpha is moved, right? Looks like alpha omega is moved. So what should it be?
Omega square root of 4 alpha.
Well, actually, it should be. This one isn't in the table, so this one was a little bit harder to see. But you can tell, where does omega go? Omega goes to omega squared, which means omega squared goes to omega, right? And what am I trying to look at? I'm going to look at alpha squared omega, or alpha omega squared. Alpha omega goes to alpha. And so alpha omega squared goes to, well, I guess I should have, this goes to, well, this is alpha omega times omega, which goes to alpha, and omega goes to omega squared. So that's fixed. Okay, what about this one? What is fixed by this? Just the omega. This permutes all of the stuff except omega. And, well, any guesses is what is the field that is fixed by all of S3? Only Q is in this example. Now let me make one more observation. What are the indices here? Well, the index of the indices here is the orders of group, right? What's the index here? 2, and these are all 3. What happens here? Well, to go from here to here, this is degree 3, 3, 3, because these are all the 3 roots of the cube root of -2, which is an irreducible polynomial. This is the root of x squared plus x plus 1, which is degree 2. This has a degree 3 extension because you've got to join the alpha, and all you need to get from here to here is just omega. Notice that the numbers match exactly, and this is not a coincidence. This is essentially the statement of fundamental theorem of Galois theorem right here. And I will give that to you formally next time. But this picture, if you remember this picture, gives you exactly what you need in the fundamental theorem. You have fields corresponding to subgroups with the indices matching, and there's also some other technical conditions on them. By the way, what's different about this subgroup as opposed to these two? Anybody know what's more interesting about this subgroup of S3?
It's normal.
It's normal, right? As opposed to these other two. This extension is Galois. Well, I'm sorry, this extension is Galois, and these two aren't because they're not, or these 3 aren't because they're not normal. We'll see that connection. Okay, questions? All right, well, I hope that paints a bit of a picture for you. You all have a good one, and we will see you on Wednesday. And some of you I may see in a few hours.